Okay, welcome back from spring break. So I guess based on what's happening with homework, as a whole, you guys have a lot to do for the second half of a semester. So good luck with all that. And in my not so humble opinion, this is a part of the course that I've been waiting for. Because I just happen to find the previous stuff that I've been covering less interesting than what's to come. Because it's all about iterative methods now. First, iterative methods for solving AX equals B, and then methods for computing eigenvalues, which are all iterative in nature. And I just happen to think that iterative methods are cooler. But, okay. So we're getting to chapter 5 in the notes now. Now, after spending quite a bit of time on direct methods for AX equals B, and Gaussian elimination, forward and back substitution, also Cholesky factorization, or LDLT. After spending so much time with methods, now I'm going to give you some very compelling reasons not to use any of them, at least for certain cases. So, I guess some might find it controversial of me to write this in the board and have it posted on YouTube, but what the hell? Why direct methods suck? So first of all, suppose you have some idea of what the solution should be. Like something that is a halfway decent approximation to the solution, and you just want to improve it to make it a more accurate approximation of the solution of AX equals B. Well, a direct method has no mechanism to take advantage of that knowledge. And it's not unreasonable to expect that you would have, in certain situations, a decent, you can call it an initial guess. For example, the application I've given before, where you are solving a system of ODEs using an implicit time-stepping method. So as you go from time step to time step, your solution from a previous time step is a good approximation of your solution at the next time step. How good an approximation depends on how small your time step is, but you'd like to be able to take advantage of that to help solve the system that you need to solve at each time step. If you're just using Gauss elimination, it's like, I don't care about that knowledge that you have. So that's number one, and I got more. And if you use Gauss elimination and substitution, it will compute the exact solution to AX equals B, except for round-off error that accumulates. But there are situations where maybe you don't need extremely high accuracy, because what if your system AX equals B already has some error into it? What if A is erroneous? What if B is erroneous? If the entries of A or B can be off by, say, 1%, then your solution is going to be off to a certain extent, no matter what you do. So, do you really want to go through trouble of solving a problem exactly? What if you would be happy to settle for less accuracy in exchange for less computational effort? So you want to be faster about it, and you're okay with taking less accuracy in exchange. Well, direct methods don't allow you to do that either. So direct methods are very inflexible. There isn't any way to say halfway through the process, oh, I have enough accuracy, it's Miller time, we're done. Can't do that with direct method. There's no mechanism for saying, oh, this is good enough. Okay. Now, I have even more. What if your matrix is sparse? Meaning most of the entries are 0. So that could create a problem for Gaussian elimination with pivoting. So PA is equal to LU. And I mentioned this phenomenon before when I talked about banded matrices. So whatever structure a matrix has, if it's sparse, then row operations, and especially if there's pivoting involved, can cause what is known as fill-in, where you create new non-zero entries that weren't there before. So elimination can destroy sparsity and increase your computational effort. So iterative methods don't mess with sparsity. And one more. What if you don't have A explicitly? Explicitly. In other words, you don't have every single entry Aij of A. And that seems crazy, like why wouldn't you have a matrix if you're solving Ax equals B? So instead, you have some function f where your input is a vector x, your output is a vector y, that happens to equal ax. So in other words, your function f implements the matrix vector product, but it does so without having storage of all the entries aij. Maybe it doesn't give you that information. Now, what you could do is you could plug in x equal to every column of identity, E1, E2, etc., and get all the entries of A that way. But that's a waste. You have to call it n times. So you don't want to do that. So it'd be nice to have methods that can still solve A equals B, even if this is your only representation of A. All right. So now that I've firmly established that the direct methods we spent so much time covering, in fact, suck, I can start talking about alternative, iterative methods. Okay. Now, there are two types of iterative methods that I'll cover. So the first are called stationary iterative methods, and these are ones that I'll spend time on today. Where the stationary iterative method has this general form. Each new iterate is equal to some function g where you plug in the previous iterate. And then once you have this, you just keep plugging it in to get the next one. You just keep going until your iterates converge, where your initial guess, x naught, has to be chosen in some way. If you don't have any particular way of choosing it, then you might as well just choose it to be 0. Okay, now, those of you who've taken classes with me before, well, depending on the class, this should look familiar to you. Can anyone tell me what this is?
Yeah, looks like
Fixed point iteration. Yeah, it's exactly that. Now, in 772, fixed point iteration was used to solve a single nonlinear equation, and it can be generalized to solve a system of nonlinear equations. Here we're dealing with a system of linear equations, but the same idea applies. And what you'll see is that some of the similar theory applies. Okay. So the idea is that hopefully xk will converge to the exact solution x, which is called a fixed point of this equation x is equal to g of x, also known as a stationary point. Thus the name stationary iterative methods. Okay. Now, the other kind, that is predictably called non-stationary, is a method of this form where each new iterate is equal to the previous one plus some parameter, which I'll call alpha k, times a vector, which I'll call pk, and this is called a search direction. So these different non-stationary methods choose some vector pk, thinking that searching in that direction of pk will lead to a better approximate solution based on some criteria. And then you have to scale that by alpha k to determine, once you've chosen your direction, how far do you go in that direction to improve your solution as much as possible. So methods such as the conjugate gradient method is the best known for positive definite matrices, is what I'll spend a lot of time on. And then there are other efforts to generalize this to matrices that aren't symmetric positive definite. Okay. So now, with that in mind, I will go into more detail on stationary iterative methods. Now, so to refine the form that I had earlier, I have xk plus 1 is equal to g of xk. It's not going to be more specific about what g looks like. I'm going to write my matrix A that I'm trying to invert as a difference of two matrices, m minus n. And I'm going to call that a splitting of A. So different stationary methods that I'll show you are based on different splittings. So at first I'll talk about, once we chose a splitting, then how do we build an iterative method from it. So then if I have AX equals B, I can write that as m minus n x is equal to B. And then I'll move the nx term to the other side. So I have mx is equal to nx plus b. And then I'm going to make the assumption in my splitting here that at least m has to be non-singular. So now I can multiply through by m inverse. So x is equal to m inverse times nx plus b. So now I've described my equation ax equals b in a different form. X is equal to some function of x. So this is my g of x. So now I have this in a fixed point form. So I can come up with criteria for convergence. I can prove for a given splitting that this will converge or not. Okay. So with that in mind, I now have I can now describe my iterative method. It is m times x k plus 1 is equal to nxk plus b. So this is the general form of a stationary iterative method. Now, I could multiply both sides by m inverse, and it looks exactly like this, xk plus 1. So this is equivalent to xk plus 1 is equal to g of xk. I'm writing it this way to make clear about what we're doing is we're not actually going to multiply by m inverse, because I told you how I feel about actually explicitly using the inverse. What we do at each iteration is we solve this system of equations by appropriate means. So we are using a direct method now, But generally what happens is we're not using Gaussian elimination per se. M will be a simple matrix to work with. So that's another criteria that we need, because we're going to be solving this kind of system several times. So we don't want to trade a direct method where you're incurring like 2/3 n cubed floating point operations, solving it once, to a method like this where we do the same thing any number of times. No. It should be, the system should be easy to solve for this to be practical. For instance, M could be lower triangular, upper triangular, or better yet, it could be diagonal. So matrices like that. In fact, that's what will happen in the methods that I'll show you. Okay. Other questions so far? Okay. Now, before I get to any specific splittings, I'd like to come to some criteria for convergence in the general case, to be able to prove that a given method converges. Now, if I take my iterative method, this general form, and then I also have what the exact solution satisfies. That mx is equal to nx plus b, that I wrote on the previous board. And then I subtract these equations. Okay. And I'm also going to introduce this notation. I can let the error after k iterations be the approximation minus the exact. So if I subtract these two equations, I'm going to get m times the difference between these two, but that's ek plus 1. And then here I have n times the difference between these two, so that's going to be ek. And then the b's will cancel. So in effect, I can say how each error relates to the previous error. It's m inverse n. So each error gets multiplied by m inverse n from one iteration to the next. So we want to make sure that this error goes to 0. Now, I've talked about this before where we have a sequence of vectors that's defined by taking each, like you choose an initial vector, and then each new vector is obtained by multiplying a previous one by some matrix. So, so in general, if xk plus 1 is defined by axk, then xk converges to the 0 vector. Well, there's two criteria I gave you guys a long time ago. There's a sufficient condition, so this will happen if something happens. And there's also an if and only if. And yes, it was a while ago, so I can understand if you guys might not remember, but I can dream. So, so what would be, they would give me a condition that I've stated before on what it takes for a sequence of vectors like this to go to 0.
If x is equal to 0, or like if it is the 0 vector.
Yeah, we can't count on that. We'd love x and we'd have the exact solution. Yes, it does. Yeah, I'll take that.
If A, let's see. A is a diagonal matrix. For triangular.
No, so,
Inverted, non-singular. We can say.
I mean, I can do this identity.
no, that won't work actually.
Maybe like a determinant.
No, that can go either way.
Okay, throw us some hints.
Okay.
As
Okay.
derivatives? I mean,
Oh, no, we're not getting calculus on this one. Okay. So, take a norm of both sides. And keep in mind, you want the norm of x to keep getting smaller and smaller, to go to 0.
Something about A.
Yeah, it has to be property of a, because x can be anything.
Yeah.
Something has to be less than 1. Actually, that applies in both cases.
The norm.
Yeah, any norm of A is a sufficient condition, not necessary. So there are cases where a norm of A can be greater than or equal to 1, and still, still go to 0. So what other property of A could be less than 1 to make it an if and only if thing? Yeah, what's another way to describe a matrix by a single number?
The rank.
What?
The rank.
Not that number.
Just. You said one number.
I know. We already said determinant. and you said
Yeah.
no.
No.
One number?
What?
One number? What do you?
There are
No.
okay. There are different formulas for the determinant. What are some of the simpler ones?
Like for a 2 by 2.
Or actually any size matrix.
So.
trace minus square, trace square minus determinant.
Or you think of eigenvalues for 2 by 2 case, but
Oh, you're enough.
Oh.
My bad.
eigenvalues. That's what
Yeah,
eigenvalues.
products of the eigenvalues.
Yeah, determinant. Yeah, but what? Okay, so something related to eigenvalues is what goes here, but not to determinant.
I mean, is it the sum of the eigenvalues? That's or the product of the eigenvalues?
Nope.
Well, the
I mean,
product
is that
would
what
be
just
determinant.
Yeah.
The product of the eigenvalues is the determinant.
Yeah.
So the greatest eigenvalue.
Yeah. Spectral
Oh,
radius.
yeah.
Yeah.
That's all we had to say.
Oh, he did.
I did, but
You wouldn't say it out loud.
I
That's how it sounded, right?
Okay. Well, remember my hearing
But I
sucks.
wasn't too pumped.
Oh, okay.
You wouldn't have.
We literally said
Wait, what's
everything.
the
You could have just said it.
Yeah.
Oh,
We're gonna do everything.
Okay. Well, that was fun. So convergence happens if and only if the spectral radius of m inverse n is less than 1. Now that can be difficult to prove, but if you can instead prove that some norm of m inverse n is less than 1, that'll at least be sufficient for convergence. Okay. So now I'm about to get into specific splittings. So I'm going to define a few matrices here that are parts of A. L plus D plus U. So D is the diagonal. Well, I'll use my shorthand. So the diagonal goes into D. The strictly lower triangular part goes into L. The strictly upper triangular part goes into U. So L and U do not include, they have 0 diagonal entries. So this includes Aij for I strictly greater than J. This includes Aii. And then U includes Aij for I strictly less than J. So we're partitioning A into these three matrices that'll make it easy for me to describe certain splittings. Okay. And the thing is, all you have to do to define a splitting is say what M is, because A is equal to M minus N. So once M is determined, then everything else of A goes into N. So my first stationary iterative method is called the Jacobi method. So what I do is I define M to be just D. And therefore, N, which is equal to M minus A, turns out to be minus L plus U. So in other words, I can say that each iterate is equal to D inverse times minus L plus U xk plus B. Now, in this case, the matrix M is supposed to be easy to invert, and it certainly is because it's a diagonal matrix. All you have to do is take your vector and divide by each component by the corresponding diagonal entry. So what I'm going to do now is write this out component by component. So you can see like how the first component of xk plus 1 is computed, then the second component, and so on. And this is closer to what you would put in code. I mean, something like that I just written there, that would be easy to code up in MATLAB. But it's more interesting to look at things on a component level to understand how the method behaves. Okay. So if we compute all the components of xk plus 1 in order, so I have xk plus 1 component I. So, okay, so multiplying by D inverse, you're just dividing each component of a vector by a diagonal entry of A. So you have 1 over Aii out front. This comes from the D inverse bit because D is this A11, A22 down to ANN. And then once multiplying, well, first I'm going to write B, so I have BI. And then I have minus L plus U times xk. Well, that's the same as computing minus AX, okay? Except you're leaving out the diagonal. So I can use a formula for a matrix vector product. So to leave out the diagonal entries, I would say J is not equal to I. And I'd have Aij xk component j. So this is what Jacobi method looks like, written out component by component. Okay. So any questions about how this was obtained from a previous form? Now, I'm going to write this a little bit differently to expose what you could argue is a weakness of the Jacobi method. I'm going to take the sum and break it up into two. So first I want to have j strictly less than I. And then I have the sum over j greater than I. And what I'm summing is the same expression. Okay. Now, I'm going to assume that I'm computing these components of xk plus 1 in order, starting from I equals 1, 2, 3, all the way down to n. Now, well, okay. So can anyone tell me, if I'm computing them in order, what is the, what do you say is pretty inefficient about this sum right here, as opposed to this one? So if I'm computing first component, second component of xk plus 1, what is wrong, if you will, with this sum?
I mean, it's a diagonal matrix. Is it symmetric also?
We don't have, well, the diagonal part we only use here. Here we're making use of the off-diagonal entries of A, and,
Right.
we don't know about symmetry.
Okay.
All right. As a hint, it has to do with these superscripts that I have here. Well, the key assumption is that you're computing these components in order from 1 to n. Otherwise, what I'm saying would not apply.
Well, the j is less than I is your lower triangle part.
Yes.
I guess I just don't know what x I to k plus 1, like where that would fall in the.
So what's happening is like, because what you're trying to do is you're basically updating xk to get xk plus 1, and you're doing this on a component by component basis. So let's suppose you're like in the middle of this vector. So you've already computed like the first several components. You're down somewhere in the middle of it. Like say like I is equal to 10, let's say. So then you're looking at the components numbered less than 10 for this sum, and then the components numbered greater than 10 for this sum. And you have your xk, and you're using that to compute entries of xk plus 1, going from top to bottom.
I mean, do you need all of the ones that are, like if you're looking at the 10th element, do you need 1 through 8, or do you just need the 9th?
Well, that would depend on the structure of A. Like for instance, let's suppose A was a tridiagonal matrix.
Yeah.
You would need the one right above it.
Yeah.
and right below it, but nothing else. But we can't make any assumptions about the structure of A. This isn't about properties of A.
Okay.
But in terms of what we've computed up to this point, sequencing is key here. That I have this vector xk that has components x1k, x2k.
Okay, well, wouldn't xk have all of the previous ones in it already?
Well, yeah, we can assume we have these. And now what's happening is, after already computing all of this, then we move to compute xk plus 1. And let's suppose, in this situation, we've already computed these down to a certain point, let's say the first 9 components. And so we have them already. And then the rest of this, we don't know yet. Nothing's been filled in here. And now we're in the process of saying, like, say, I equals 10. So think of this as what I've written here that's the information that is available to you right now. So then what's happening is, as I go to compute 10th component, okay, I have 1 over A10, 10,
Is
B10.
this last symmetry?
So there's no symmetry.
No, I thought it would too, but. Okay, good. I finished. Okay. I'm trying to figure out where, like, I know it has something to do with J being less than I. I'm just trying to, right?
Yeah.
I'm just.
Yeah, so if this is what you have so far, and the idea is, this is something that's you're wanting to converge to x, so presumably this would be closer to x,
Yeah.
but you don't have a whole thing yet, you only have this part. So now you go to this sum, and what part of xk are you using in this sum?
Everything up to 10?
Yeah, that part. Yeah, okay, so you're down here. So
you never get to actually figure out the 10th element or anything below it?
well, or at least, okay, this part down here, you're going to use over in this sum.
Right.
So that'll play a role, but what's happening is these elements are being used here.
But we already have them,
Right.
so it's kind of just, it's a waste of,
It's a waste
yeah, okay.
because we have better elements here because this is closer to the exact solution, presumably. So that's the flaw in Jacobi. Now it's an arguable flaw for reasons I'll get to in a moment. But assuming you're computing these components in order from 1 to n, you're using old information here. So let's try not doing that. Let's fix it and use for this sum. And here we have no choice. We don't have these elements of xk plus 1 yet, so we'll leave that alone. Here we'll change that to xk plus 1, and that, well, that's not the Jacobi method anymore, that's a whole new method. Called the Gauss-Seidel method. So I'm going to do the opposite what I did with Jacobi method. Jacobi method, I wrote it as, here's the splitting, here it is in matrix form, here it is in component form. But then we use the component form to figure out how to change it. So I'll write Gauss-Seidel in component form, and then we'll try backtracking to writing it in matrix form, figure out what is the splitting in this case. So I just make this little change, using xk plus 1 for the components for which we can, and then still using xk for components where we can't. So that's Gauss-Seidel. Now, well, first, before we look at other forms of it, so the pro is that it uses updated information about x, k, plus 1. So it's often, I wouldn't say always, but it often converges more rapidly. Okay. But it's not always a good thing, because that relies on computing the components in order from 1 to n. That means you cannot compute components in parallel. Whereas with Jacobi, you can. So this is actually a double-edged sword.
So are we going to talk about when it's better to use which one?
There's not a whole lot I can say, unfortunately. Yeah, that's one thing that I don't like about these two methods is that you can't say, like, oh, for this class of matrices, this is always better or something like that.
Yeah.
Yeah, but there's certain examples where, I've seen examples where, for Gauss-Seidel really is much faster. I haven't really seen it go the other way. Like, if Jacobi wins, it like kind of wins by a nose. I think generally Gauss-Seidel is more often used. Plus, the next method I'm going to show you is a modification of Gauss-Seidel that would beat both of them generally, and is more flexible.
So they have the same like accuracy.
Well,
I mean,
yeah. Well, the thing is, since for certain classes of matrices, they're going to converge,
right.
but then it's a matter of how quickly will they. So really, it's a matter of if you can at least be assured that the method is going to converge, then you want to try. Then what method is going to get you there faster? So that's why convergence speed is where the conversation generally heads.
Are there like things to look for in matrices? Like, is there something common in matrices that you use Jacobi method over like? There's something?
Yes, and I will come to that.
Okay.
Yeah. Okay.
I don't understand what you mean by parallelizable.
So in this method, like since like the example I gave before, suppose I equals 10. To use this method, that relies on having computed components 1 through 9 of my new iterate. So I will have had to have done them first. There's a prerequisite. Jacobi, there's no such prerequisite because even though it's using old info, I could compute the components of xk plus 1 in any order that I wanted, or I could, better yet, I could compute them simultaneously.
Using array operations or whatever, right?
Exactly, yeah. Like certain parallel or vector architectures, you can do that, but that is not available in this case. Order matters. Okay. Now, let's see what is the splitting in this case compared to the one for Jacobi. And so we'd like to write this in matrix form. So I'm going to take the inverse, the D inverse, and basically I'm going to multiply both sides by D. So I have dxk plus 1 on the left side. And on the right side, I have B. And I want to describe both of these as matrix vector products. And you, Abby, you hit on it earlier when we were sorting through that. What part of A? Yes, the lower triangular part, L xk plus 1. And therefore this term, yeah, is minus U xk. But now we'd like to have xk plus 1 on the left side. So I'm going to move this to the other side. So now we have d plus L xk plus 1 is equal to minus u xk plus b. And now we can see what the splitting is. So your m is, instead of d for Jacobi, it's now d plus L. And then your n is equal to minus u. Now what I find really interesting about this is, as I said before, the matrix M needs to be easy to invert. Now, diagonal matrix, you can invert in order n operations. Lower triangular matrix, which is what this is, that takes order n squared, because you have to use forward substitution. So what seems really odd is I've now made my system an order of magnitude more work to invert. But if you look at the formula for the component-wise for Gauss-Seidel versus Jacobi, really the amount of work involved is exactly the same. It's just that you're using different pieces of information. So that seems kind of contradictory until you keep in mind that the work involved in inverting this lower triangular matrix is kind of equivalent in a way to performing a matrix vector multiplication. So, so in other words, here, this part that looks like a matrix vector product is essentially a forward substitution. So that's why. So really, the work involved is just being classified differently. Even though the total amount of work between Jacobi or Gauss-Seidel is exactly the same. Because for both methods, the amount of work is order n squared. Whether it's a matrix vector product or a forward substitution, it's all the same. Okay. Now, my last comments on Jacobi and Gauss-Seidel. There are certain classes of matrices for which we know these methods can be proven that these methods converge. So first, Jacobi is guaranteed to converge if A has this property. There's a lot of adjectives here. Strictly row diagonally dominant. And what that means is the absolute value of each diagonal entry is strictly greater than the sum of the absolute values of all the off-diagonal entries in its row. So strictly row, because we're going across the same row, diagonally dominant. So every word is justified. And because what happens in this case is, if you have this, you can prove that the infinity norm of m inverse n is strictly less than 1. Because, well, the m inverse, that's easy to handle because you have, you're just dividing by AII. Because m inverse n, you can write down what it looks like. It's, well, the diagonal entries are all 0. The off-diagonal entries are actually minus AIJ, actually put the minus up front, AIJ over AII throughout the matrix. Because if you divide both sides by AII, you have that this sum, which is a row sum of this matrix, is less than 1. So what is the infinity norm of a matrix? It's the maximum row sum, and they're all less than 1. So quite an easy proof in that case. Meanwhile, and I've seen this proof a long time ago, but unfortunately I don't remember it, so I won't be able to do it here. Gauss-Seidel is guaranteed to converge if A is symmetric, positive, definite. Although actually, I might have a way to prove it later based on other stuff in my notes. I'll just check on that. Okay, so these are two categories of matrices where we know we can use one method or the other. Unfortunately, I'm not aware of other similar sweeping statements with these two methods, but it's something. And these are kind of matrices that tend to come up in certain applications, like involving differential equations. Okay. Now. Okay. So now I have a third stationary iterative method. That's a modification of Gauss-Seidel. That's called successive over-relaxation. That's a bit of a mouthful, so we just call it SOR. Now, the general idea behind SOR is if I write xk plus 1 in this form, xk plus xk plus 1 minus xk, where all of these come from Gauss-Seidel, you can think of this quantity here as the step you're taking from xk to xk plus 1. So the idea behind SOR is, what if you might be able to accelerate convergence by going further along this direction? If you take this direction from your current iterator to your next one, what if you go further along that direction to a certain degree? Maybe you can get to the exact solution faster. So what you do is you multiply this by a parameter. So you think in terms of your new iterate is your old iterate plus some parameter omega times the iterate that you would get from Gauss-Seidel minus your previous iterate. So omega is called the relaxation parameter. Now, if you choose omega to be greater than 1, then that's called over-relaxation. If you choose it to be less than 1, you can call that under-relaxation. But for whatever reason, even though you could choose omega to be less than or greater than 1, we always call the method successive over-relaxation. Generally, omega is chosen to be greater than 1. That seems to be advantageous in more situations. So with that in mind, here's the splitting for SOR. So you have a lower triangular system still to solve, but now omega is multiplying your lower triangular part L. And then you have, on the right, you have 1 minus omega d minus omega u xk plus b. So this is your m, and this is your n. Okay. So one way to think about this is if you took, oh, whoops, I forgot omega. Omega b. So one way to look at this is suppose you took Gauss-Seidel and multiplied everything by omega, but then you added a d to both sides, and you took the omega d you got from Gauss-Seidel and moved it to the other side. That's one way to kind of see how you would get SOR from Gauss-Seidel. Now, so SOR with omega equal to 1 is Gauss-Seidel. So this reduces to that. And you can see that if you will go ahead and substitute omega equal 1 here. All right, so Gauss-Seidel is just a special case. Okay. Now, it'd be nice to have some guidance on how you can choose omega.
Is there any relation between omega and grid points?
Omega and what?
Grid points.
Um,
What's the difference? I mean, well,
Okay.
I've heard that name, but
Oh,
I cannot really feel it.
A relaxation parameter?
Yes.
Actually, I brought it up for in 772 for fixed point iteration, where you're defining your g multiplied by a certain scaling factor. So relaxation is a very commonly used term when it comes to solving equations by iteration. It's also used in multigrid. And in that case,
But there is no relation between relaxation parameter and size of the grid points.
well, that may affect the choice of the relaxation parameter, but otherwise not really. This is more general than that. Okay. So, if I look at the iteration matrix, which you can do for any stationary method, I'll call it T omega, and that's just your M inverse N. So I take the M inverse over there, so that's D plus omega L inverse, and then we have 1 minus omega D minus omega U. Okay. So then what I can do is, keep in mind, this is lower triangular. This is upper triangular. So that makes it really easy to compute the determinant of this. So the determinant of T omega, well, the determinant of a product is a product of determinants. The determinant of an inverse is the reciprocal of the determinant. So for this part, I'd have 1 over. Now, this is a lower triangular matrix. How do you compute the determinant of a triangular matrix? It's easier than for a general matrix.
Multiplication.
Yeah, multiply the diagonal entries. What are diagonal entries? They're just the entries of D, because omega L, that's strictly lower triangular. It's not going to contribute to the diagonal. So I have the product of AII. And then over here, similar idea, only this is going to make a contribution. So now I have the product of 1 minus omega times the product of diagonal entry, times each diagonal entry. So the diagonal entries will cancel. And so no matter what your matrix is, the determinant of your iteration matrix is always 1 minus omega to the n. Now the thing is, you want the spectral radius of T omega to be less than 1. what we have here, this is the product of all of the eigenvalues of T omega. So the only way to make sure if the product of all of these is equal to this, and you need each one of them, these eigenvalues individually, to be less than 1 in absolute value, we need absolute value of 1 minus omega to be less than 1. Okay. So that means that omega must be strictly between 0 and 2. So omega between 0 and 1, that's under relaxation. Omega between 1 and 2 is over relaxation. Okay.
What is a spectral radius?
What?
Spectral radius.
Oh, that's a magnitude of the largest eigenvalue. Okay. Now, in certain cases, limited cases, we can prove what is the best choice of omega. So if, well, I'll give you an example. If A is symmetric, positive, definite, and tridiagonal, so that certainly does come up in like certain differential equations, for instance. The optimal omega turns out to be 2 over 1 plus square root of 1 minus the spectral radius of Tj, where Tj squared is d inverse times minus L plus U. That is the iteration matrix from a Jacobi method. So if you can figure that out, or you can at least estimate it from, because you can compute the infinity norm of the Jacobi matrix, which is greater than or equal to the spectral radius. So there are certain cases like this where you can actually figure out what the best choice of omega is. And because we're assuming that the iteration would converge for a Jacobi method, that this spectral radius should be less than 1, that would imply, just checking it algebraically, that omega is between 1 and 2 in this case. But unfortunately, generally, just have to play around with omega and see what works best, unfortunately. But because there are some situations where if you try several values of omega, and like for a given system, and see how many iterations it takes to converge, that you would find that there is a minimum to, like, you think of the iteration count as a function of omega, or the spectral radius of iteration matrix as a function of omega, that there's a behavior like this, where there's a local minimum. Okay. Now,
And the very last line, what is that? T sub what?
T sub J.
J, okay. Capital J.
So this is the reason. Oh, excuse me.
Oh, they both should be uppercase. I think I have lowercase j in the notes, which they can seem like a index, but it's not.
So this is the reason that you said why people use over-relaxation. It's because maybe the matrix is symmetric, positive, definite.
Yeah, and I think this is one situation where over-relaxation is called for, but there seems to be other situations too. Just what I've observed in practice. I've rarely seen this case where it's better to choose omega less than 1. Okay. Which makes sense because by choosing omega greater than 1, you're going further in that direction towards your exact solution. So it kind of makes sense that you will choose a greater than 1. I should mention that SOR was actually developed by a student for his doctoral dissertation back in 1950. His name is David Young, and since it's such a famous dissertation, because that does not happen often, that such a significant method is developed by a student, you can look that up. You can get a hold of his dissertation. And I think they've modernized it because back then, in 1950, we didn't have LaTeX or anything like that. So I think it was all like done on a typewriter and everything.
So what made his method more popular?
Just how well it worked.
I mean, he has to kind of introduce his method to public.
Right.
Kind of.
Yeah, but I guess it goes to show that if you can show pretty striking results, at least for certain systems, that since presumably since Jacobi and Gauss-Seidel methods like that would have been the ones generally used at the time, and so hey, look, here's my method that does so much better than those. That's going to get some attention. So. Yeah, so something for you all to aspire to, because you just never know. Okay. Yeah, I really do want to prove something about positive definite systems, and I have it in my notes. So I think, that'll take too long for now. But so this is a good stopping point, and I will pick up with that on Thursday.